I'm Jo Dunkley and I'm a professor of physics and I study the universe. Welcome to my exp. So we have this component in the universe that we call dark matter that we don't yet know what it is, but we think we understand how it behaves. So let's think about this. So we think that dark matter is stuff that follows the law of gravity but doesn't interact with light at all or with the particles of our bodies and our planet and anything. What does that mean? It means that if dark matter is a new kind of particle, it can travel through our body, through anything. It doesn't interact with the regular atoms we know of. But it does obey the law of gravity. And so we can imagine, for example, if we were to suddenly turn the sun into dark matter and somehow make it the same location and shape, the Earth would still orbit around it because we orbit the sun because of the gravity of the sun. And so a dark matter version of it, we would still orbit around it, we just couldn't see it. This idea actually lay dormant for a number of years and was really picked up on by astronomer Vera Rubin. And she and her colleague Kent Ford were looking not at whole clusters of galaxies, but just individual galaxies, spiral galaxies, a little bit like our Milky Way, where a spiral galaxy spins around, again, because of the gravity of all the stuff in it. And if a galaxy were only made of stars and also some gas and some dust, stuff that sends out light, then you can make a very specific prediction for how fast the stars in that galaxy should orbit around based on the gravity of all the stuff that you can see. What Vera Rubin and Kent Ford showed is that the stars at the edges of the galaxies were actually orbiting much too fast for just the visible stuff in the galaxy. And the inference then was that there was actually not just the stars and this gas and dust that's in them too, but a whole lot of invisible matter. And on average, 5 times the mass of all this visible stuff. And so you can imagine our Milky Way disk of a galaxy is not just the stuff you can see, but also an invisible kind of halo or almost sphere that the stars are embedded in. Now, at a similar time, there was theoretical work going on by astronomers, including Jerry Oestreicher and Jim Peebles, to show that the galaxy would only keep its disk shape if there was this invisible dark matter around it too. So Vera Rubin was such a pioneer of this field. As a woman at that time, she couldn't go to any university she liked, but ended up having a very successful career, but had to keep pushing to do what she wanted to do as a scientist. Partly that included doing evening classes while juggling childcare, and then being the first woman to be allowed to use the large new telescope that was available at the time. And at the time, only men were allowed to use it. So she really pushed forward on insisting that she be able to use the telescope to make these measurements of the rotating galaxies. What's wonderful now is that there's a huge new optical survey. So we've made our new map of the dark matter. There will be another new map coming from the measurements of galaxies being distorted by the dark matter. And that will be made by the Vera Rubin Observatory, now named for her. And many of us were just so delighted when this really important new observatory that's in Chile and just getting underway now carries her name. So we've been making this new map of the dark matter, and we've been doing it through looking not actually at how things spin around, as was done earlier on, but instead at looking how light gets bent around invisible stuff. So if I was a source of light and there was a big invisible mass in front of me, the light, and this is now Einstein's gravity tells this to us, the light would get bent around it. If I could measure how much light gets bent, I could infer that there's something there. That would be my new kind of weighing scale or way of seeing the invisible, is by using a backlight and seeing how much the light gets distorted. Because the heavier something is, the more a ray of light gets its path bent. Now we get to see this in beautiful visuals in work actually that my team don't do, but I love to look at, which is where galaxies themselves get bent around the invisible matter. And this is called strong lensing, where there have been beautiful images recently from, well, most recently from the James Webb Space Telescope, but also by many other telescopes, where you see these arcs of light, where the galaxy that was started off kind of like a sphere or an ellipse, a spheroid, is stretched out to this arc that goes around, that comes from the light bending around the invisible mass. I've been working on the Atacama Cosmology Telescope project, which is a team of about 160 people internationally. We have been measuring the bending of the light, not where the backlight is not now galaxies, but the backlight is this cosmic microwave background. It's that initial primordial light that's coming from the beginning of the universe. And that's so powerful because it's the furthest light we can see. It's coming to us from all around the sky, and it's been traveling for 14 billion years, almost the whole age of the universe. And so it's been gently bending around all of the invisible matter in the universe. So by using that most distant backlight, you can weigh, on average, the sort of total invisible matter around us, in this kind of like sort of sphere around us. And that's what we were doing with a new image of the microwave background that we made with the ACT telescope. And I love this project because it brings together 160 people where we all play different parts in that sort of long effort. And so some people are involved in building very sensitive detectors to make capturing the light possible. Some people have installed and made work the telescope in Chile, 5,000 meters up on a high mountaintop. Other people have gathered that data and kept the telescope running. And then we take the data that scans the sky for years on end, and we turn that into a new image of the microwave background. And because the telescope that we have in Chile has a dish that's 6 meters in diameter, it can see this image of this early universe in higher fidelity, higher resolution than was previously possible. And that's allowed us to subtly tell how it's been distorted by the invisible matter on its journey to us. So many of our colleagues are involved in, making that map. And then other parts of the team are then involved in trying to figure out how much it will have been distorted and therefore make a map of how much dark matter there must be at any point in space that was doing that distorting. The new map showed that the behavior of the dark matter on average through the universe does seem to be behaving as we would expect in the standard cosmological model. And there had been some concerns about whether that was indeed true, that maybe the behavior of dark matter was changing with time and behaving in some different way. But what we found really held up the standard cosmological model. It sort of characterized well the dark matter part of the invisible universe. But it hasn't fully weighed in on the other dark component in the universe that we call dark energy. So the ingredients of the universe we think are the regular matter that we're made of, this dark matter component that is maybe a new particle that behaves, just follows the laws of gravity. But there's this other part of the universe's ingredients that often gets called dark energy, that's been kind of dominating the energy density of the universe in the last half of its history, so for the last 7 billion years or so, 7 or 8 billion years. And we don't yet know what that is either. We think it might just be the energy of empty space. It's often called lambda or a vacuum energy. was actually part of Einstein's original equations. And again, it's not something that's visible to our eyes or our visible telescopes, but it seems to be an energy coming from the energy of empty space itself. But we think it's rather different. It's different to the dark matter. But because we don't know which either of them are, we can refer to them as dark matter and dark energy. And our telescope has shown that what we see is very consistent with it being this vacuum energy, but we'll have to gather more data to wait and see.